In this video, I'll cover 8 advantages and 8 disadvantages to using decision trees. Now, everything I'll talk about here has already been covered in an article that I included on my blog. There's a link to that blog article in the description below. So let's start off with the 8 advantages. So the first thing is that decision trees tend to be relatively easy to interpret. So we can actually just draw out the structure of the algorithm. It just forms something like a flow chart. And this is something that really helps us in terms of understanding how the algorithm arrives at the decisions that it arrives at. So I covered in quite a lot of detail how decision trees work and how they can be implemented in a previous blog post. I also have a link to that blog post in the description below. I also went over that in detail in a 4-part video series on this YouTube channel. I also have that linked below, so you can also check that out as well. Point 2 is that decision trees tend to be fairly robust to outliers. Now, this depends on whether our decision tree model is well regularized. So we have to restrain how complex the model can get during training. But in general, decision trees tend to be quite good at dealing with data that contains outliers. The third point is that decision trees can handle missing values. So this is quite a neat feature of CART decision trees. Most machine learning algorithms don't have this ability, and in fact, we have to do some feature engineering or data preprocessing before applying our model to handle missing values in the data. And in a real-world data set, it's quite likely that we will end up with features that do in fact have some missing values. Point number 4 of our list of advantages is that decision trees tend to be nonlinear. And so this is pretty good because a lot of real-world problems are not linear by nature. And so we don't want to have that assumption in our model. So something like a very simple model like linear regression has built into it this assumption that the data that we're dealing with, the problem that we're working on, is linear. But for a lot of problems that we'll encounter in the real world, this assumption doesn't apply. So using a decision tree that is a nonlinear model is quite a nice option. 5, now in terms of our list of advantages, is that decision trees are non-parametric. And what this means is that this algorithm does not make assumptions on the underlying data that is used to train the algorithm. And that means that we don't have to be concerned with these underlying assumptions when applying the model. We can just apply the decision tree to the data without having these assumptions as something that we have to worry about during pre-processing or feature engineering. Our 6th advantage is that decision trees naturally handle combining different features together in order to arrive at a decision. And so if we look at the branching structure of this decision tree, if we want to see how we arrive at the prediction here, for this node circled in red, we can follow from the root node down through the tree structure, and I've indicated the different steps that the model takes to arrive at this decision with these bold red arrows. And we can see that the first decision is based on a certain feature. Now the data that this tree was trained on is on the iris dataset. So everything I refer to here will be for that data. So the first decision is based on the petal length being a certain size. Then the second decision is based on the petal width. Then we go and we make a decision based on the petal length again. Then the sepal width. And finally, we arrive at our terminal node or our leaf node. So we can see here that to arrive at any prediction, we're actually combining different features together. And so that is a very nice natural advantage to using decision trees. Our seventh advantage is that cart decision trees can also handle categorical values quite naturally. And so this is similar to the previous point that I made about handling missing values. Decision trees can also handle categorical values naturally without having some pre-processing stage beforehand that will encode the categorical values into some numerical feature set that then can be used by the model. Depending on how we implement the decision tree, we can actually just build the algorithm so that it can handle the categorical values outright. This is something that I did in a previous blog post. I've also included that link in the description below, so you can check that out. But this is a nice advantage because a lot of machine learning models would actually require that you do some sort of pre-processing to handle this. So yeah, this is pretty good. Eighth and final advantage that I'll talk about here kind of ties in some of the previous points that I was talking about, and that is that we have minimal data preparation for decision trees. So because we can handle, or we can potentially handle categorical values, missing values, just through the implementation of the decision tree itself, that means we don't have to deal with it in the pre-processing stage, but also because this is a non-parametric model, so we don't have to worry about the underlying assumptions in the model algorithm when doing our training. This means that we don't typically have to do too much in terms of data preparation. Another key thing to note is that because of the way the cart algorithm works, in that we look at each individual feature on a one-by-one basis, we also don't have to worry about scaling or normalizing our feature set. So now I'll cover 8 disadvantages to using decision trees. So the first one is that decision trees are prone to overfitting while training. So what we need to be very careful about is to restrict how much they can grow. Now, normally there are several hyperparameters that we can use to restrict or control how much a decision tree can grow during training. And this is very important to set properly because otherwise the decision tree will just overfit on the data, and then the quality of predictions we'll get out of it won't be that great. Number 2 is that decision trees tend to be unstable to changes in the training data. So this is an important point, and it affects the interpretability of the model that we generate. So if we look at a small example, here I have created 2 data sets that are virtually the same, except that I have just changed the number of informative features that we have. So the first data set up above has 4 informative features out of a total of 6. The second one has only 3 informative features out of the total of 6. Otherwise, the 2 data sets are exactly the same, and I've also set the random state to be the exact same value. So technically, we should be able to get the same data out of this, except for the fact that one has one more informative feature than the other. So what happens if we then train 2 decision trees on these 2 different data sets and then visualize them? Well, the first decision tree looks like this. So we see that the root node is based off of the 4th input feature, and then that branches out. So then the left branch then is looking at feature 2. The right branch is looking at feature 0, and so on and so forth. So we can look at the features that are used to discern or to split at each node, and then also the split points as well. If we look at the second decision tree that's formed up, we can see that there are quite significant changes. For one thing, this decision tree is not symmetrical. We can see that there's a missing leaf node here, whereas with the first decision tree, this wasn't the case. This tree is quite symmetrical. As well, the actual features used and the split points in each node are different. So we can see that just by changing the number of informative features by one, we get two completely different trees resulting from that. So that's something that's very important to keep in mind with your project, is that if there are any changes over, say, for example, if there are any changes over time, if you're building a model to do some sort of monitoring or something like that, if your training set changes over time, then it could affect the interpretability of your model. You can see these changes happening over time. The third disadvantage is that decision trees tend to be unstable to noise. So we can look at an example here on the screen where I have our set of input features that I generated in the previous example. And here we can see, the distribution. And now I'm going to just inject some Gaussian noise and create a second data set out of that. So we can see here, if I plot the distribution of these features, there's quite a lot more outliers in these data. And now what happens if I look at how the decision tree is structured? So if I look at this decision tree and I compare it to the decision tree that we did, that was the original decision tree without the noise, you see that there's quite a lot of differences, again, in terms of the features used in the different nodes, but also the split points at those nodes. So if we look at the first right-hand node, so this is coming from the root node down. In the original, it's based on feature 0, and it has a split point of 0.199. And if we go down to the tree that was trained on the noisy data, it's now based off of feature 4 and has a split point of 2.618. So we can see that the general flow through the data that the model is using to arrive at its decisions has now been altered as a result of the presence of these data. The fourth disadvantage we have is that decision trees are non-continuous. So by their nature, decision trees are piecewise approximations to a continuous function. So if we're dealing with a regression problem, this is something that's very important to keep in mind. So if we look at the data that has been generated here, this is just a very simple data set with one predictive feature, which is on the x-axis. And then we have one predictive feature, which is y, it's the vertical. So we have this distribution here that has some noise in it, but it's otherwise just a linear function. And so now if we want to have a decision tree regressor learn these data and make predictions, we can do that, but we have to be very careful about the quality of the results that we get out of it. So again, because of that piecewise nature, if we have a very shallow tree, so in this case, I just have a tree that's grown to a maximum depth of 3, what we end up with are these results. So in this plot, we have the original data, and that's in blue. And then we have the training predictions. So the training predictions are shown in orange, and we can see the piecewise nature of the model. So instead of forming just a continuous line up along how these data trend, we just have these steps. So this, you can see right away that this does a fairly poor job at approximating the true distribution or the true trend in the data. Moreover, because decision trees don't make any assumptions about the underlying distributions in the data. Again, they're non-parametric. It's a non-parametric model. That tends to mean that it does a very poor job at extrapolating from the training data set. So in this case, the way that I split the data was I said that, okay, I'm going to train the model on everything that is less than x equals 2, and then I'm going to try and predict the points that are greater than x equals 2. And so what happens here is that we're in an extrapolation, we're trying to extrapolate on the data, and the decision tree just simply can't do that. So in green, we have the predictions, and they just follow a flat horizontal line. They can't follow the linear trend in the data. So that's also something that's very important to keep in mind. Now, one thing we can do to try and improve upon this result is just to increase the size of our model. So here I limited the model to have a maximum depth of 3. What happens if I make a bigger tree with a maximum depth of 10? Well, now we see this, and now the orange points match up quite good with the distribution, the true distribution in the data. However, what we see here is that really what the decision tree is trying to do is map the noise in the data. And so we don't see, it's not obvious that stepwise nature, but still really what the tree is doing at this point is just mapping the noise in the data. And really what we would like to see is just it focusing in on the linear trend in these data. And so in this case, perhaps the tree is a bit too complex. It's overfitting. It's trying to map the noise, which isn't very good. So even with the bigger model, we still have the problem then of extrapolation. And so that hasn't been resolved by the more complex model, and that's what we would expect. The green points still fall flat, and they don't follow the linear trend in the data. So in this case, using a model like linear regression, which is parametric, and it assumes that our data is linear by nature, would be more appropriate. So for a classification problem, decision trees really rely on having the different classes that are in our targets to be balanced. Otherwise, the results we get out will just be of very poor quality. So we can do that in either two ways. One is during a pre-processing step, we can make sure that all the classes are balanced. Or with some implementations, you can also include class weights. And so the scikit-learn implementation of a decision tree classifier includes that. And so you can just assign different weights based on the frequency of the different class labels. Our sixth disadvantage is that decision trees or cart decision trees follow a greedy algorithm. And that means that we do not generate a model that is globally optimal. And so what we get up with is an algorithm that is more computationally efficient in the sense that we can train it in a reasonable amount of time, but it doesn't yield the most optimal solution. Number 7 is that decision trees can be computationally expensive on very large data sets. So if this is a problem that you run into, you might want to consider using a feature reduction technique, something like principal component analysis, to reduce the size of your training data. Finally, the 8th disadvantage is that decision trees can become increasingly more complex on larger data sets. So one of the strengths that I emphasized in the advantages section of this video is that decision trees are quite interpretable. And this is a very nice feature, especially if you're trying to explain your machine learning models to a set of stakeholders who are not necessarily tech savvy. However, there's a balance between this interpretability with the complexity of the model that you're producing. So at some point, the decision tree will become more difficult to interpret the more complex your data set gets. So in this figure here, we see two different decision trees, and they're both trained on the iris data set. I've just restricted the training a little bit more for the tree on the right-hand side as opposed to the left. And we can see that out of these two trees, the simpler tree on the right is much more easy to understand. You know, if we look at how the model gets to its predictions, it's pretty easy to just follow this tree to see why decisions are made. If you look at the decision tree on the left, it's more complex. And so the task of following from each node in the tree to see how we arrive at a conclusion becomes harder. Now still, this is not difficult by any means in this particular example. However, this is just used to illustrate the point that if we keep adding a lot of features and more layers to our decision tree, the more complex the model gets and interpretability will suffer. So I'd like to thank you for watching this video. If you like this content, please subscribe to the channel and like the video. You can also check out my blog article that this content is all based on. Again, I've linked that blog article in the description below. Have a great day, and I hope to see you in the next video.